Hello.
Hello, Professor.
Hello. I just wanted to see if all of you are there, which means to check whether the connection is okay or not with all of you. Maybe I can just read the names. I can just read the names and just say yes if you are there. Otherwise, I'll know that connection. There is some problem with the connection. Al-Meghari? Yeah, you're there. Okay. Amini Bakhtash? Amini Bakhtash? No. Huh? Okay. Arguello Cruz?
I'm here, Professor.
Okay. Good. Belalui Samir? No. But Minahil Adil?
I'm here, sir.
Okay, good. Then Cruz Sanchez Carlo?
Monsieur.
Yeah, good. El Sherbini Ahmad?
Yes, good afternoon, Professor.
Good afternoon. Keles Bertan?
Here.
Okay. Then Ardene Bulgan?
Yes,
Yeah.
I am here.
Good. Mengistu Sevari?
I'm here.
Okay, okay. Paul Apron? Yeah,
Yes,
you're
I'm
there.
here.
Yakub Safwan?
Yes.
Okay, good.
I'm here. Yes.
So basically what we didn't hear from two people, right? Okay, essentially, yeah, I don't know if there's a connection problem. I think that from the people who are already here, there should be no problem with the connection. But I don't know about in the different countries, how the situation is. Okay, so any questions? Any questions?
Yes.
Yeah.
Actually, when I was trying to solve the conservative quantity for SO2R group, the generator was in matrix form.
Uh-huh.
But then the other term was the differentiation of the Lagrangian with respect to x dot and y dot. So how we put this in the matrix form?
Well, I mean, actually, it was not, because what you're looking at is how the coordinates transform, right? So let me go back to that. So the equation, the conserved quantity was defined by dfj over dsa times dl over, okay, I think I was using capital L like that, dq dot j, okay, this is evaluated as potential. And what was the definition of f? F was, the transformation was qi goes to fi. That's it. Right? So now you already know, of course it is in the matrix form, but matrix form is acting on the q1, q2. Right? So q1, q2 goes to, under this transformation, it goes to cosine theta minus sine theta, cosine theta of q1, q2. Right? Acting on q1, q2. This is what we are following. You see, this goes to that. So this means that this goes to f1, f2, which is equal to that. So now you just open up the bracket, open up this matrix. So this gives you f1 is the first one. So it's equal to cosine theta q1 minus sine theta q2. And f2 is sine theta q1 plus cosine theta q2. Okay. So now you expand the theta and look at only keep up to the first order term, right? So the first one, this one simply gives you q1 minus theta q2. And this one gives you theta q1 plus q2. So now what we are doing is the s, in fact, s is as theta. So we are taking the derivative df1. So let's say if I look at the first one, So j equal to 1, that is summation over j, right? So let's just do one by one. So the first term is df1 over d theta, because s is not theta, times dl over dq1 bar. Then the second term is df2 over d theta, dl over dq2 bar. You see, now it's not, you already opened up the matrix to find what is f1 and f2, right? So df1 by d theta is nothing else but minus q2. So this gives you minus q2. And dl by dq1 dot is nothing else but nq1 dot. Remember, L was 1/2 m q1 dot square plus q2 dot square. Okay, so the first term, this term becomes that. And the second term, df2 by d theta is plus q1, right? So this becomes q1, and this guy is simply m q2 dot, which is the same as q1 p2 minus q2 p1, where pi, the momentum, is simply, this is by definition dl by dqi dot, which is of course m qi dot. Yeah. So you're right, this is a matrix form, but here what we are doing is already we are looking at this f1 and f2, right? So you multiply by the matrix on q1, q2, you get these expressions, and then linearize it. Just look at the first order, because we are interested in the first order, because at the end, after taking the first derivative, I set s equal to 0. So only the first derivative, only the first order expansion is relevant. So, okay. Is that okay?
Yes, thank you, Professor.
Any other question?
I have a simple question. For all that Zi is the universal ratio of the subsquare. For example, Z1 is equal to Z4 bar. Is it same as Z1 bar is equal to Z4?
You mean, so now you are going to the SU2
Yeah,
issue.
Yes.
Okay, so yeah, that was the question, right? Let me go through that again. In fact, that is what I left as a kind of an exercise to check whether you can, yeah. So what were you saying? Now repeat that again.
For example, Z1 is equal to the Z4 bar. Is it same as the Z1 bar is equal to Z4? Inverse ratio is also satisfied all Z5.
Z1 equal to Z4 bar. Yeah, so your question is, repeat that again. So if Z1 equal to Z4 bar is shown here, right? In this notes.
Yeah.
So now what?
If inverse ratio is also satisfied, for example, Z1 bar is equal to
Of course, yeah.
Z4.
Sure, absolutely, yeah. Because this is just a complex number. That's again a complex number. So if this equation is true, if you can take the complex conjugate of both, right? I mean, so what this would mean, suppose Z1 is a complex number. So let's call it x1 plus I x2. And Z4 is another complex number. Let's call it y1 plus I y2. No? So what this equation tells me is x1 plus I x2 is equal to y1 minus I y2, right? Because you have to take the complex conjugate of Z4. No? But this is the same. I mean, you see that when you have a complex number, the two complex numbers are equal only if the real parts are equal and the imaginary parts are equal, right? So this equation has information, it gives you two real equations. One complex equation will give you two real equations, right? So this equation implies x1 equal to y1 and x2 equal to minus y2, right? Yeah. So now you see, if you had taken the complex conjugate of this, so let's take now complex conjugate of that. So now we are looking at Z1 bar, and we are asking the question whether this is the same as Z4, right? That is the question, right? I mean, is it true or not? So what is Z1 bar? Z1 bar is simply x1 minus Ix2. And Z4 is y1 plus I1. And this is indeed equal. Why? Because we already seen that this equation implied x1 equal to y1 So these two are equal. Okay. And this one tells you that x2 is equal to minus y2. So if x2 is minus y2, this is the same as plus I y2. So that's also equal to it. Yeah. So this is a general statement. I mean, if there is a complex equation, its complex conjugate also will be will satisfy that equation, right? Because of the reason that a complex equation means separately the real parts must be equal and the imaginary parts must be equal. So if you give a minus sign to the imaginary part, it doesn't matter, right? It still is satisfied. Yeah, this is true. Yeah. Okay. So, was there any question on getting these equations? Meaning going from the set of equations which was 5.12 and 5.13. This was just the 5.12 just came from the UU dagger equal to identity, and 5.13 came from the determinant of U equal to 1 condition. And then there is this manipulation, two manipulations. One was multiply Z4 bar to the 5.13 and manipulate, and that gives you Z1 equal to Z4 bar, right? So we had, so let me just see it now. So we had Z1, Z2, Z3, Z4. So this was the U matrix. And so U dagger clearly is Z1 bar, Z3 bar, Z2 bar, and Z4 bar. And now we are looking at the UU dagger. That is if you just multiply. So you get here Z1, Z1 bar, plus Z2, Z2 bar, Z1, Z3 bar, plus Z2, Z4 bar, and Z3, Z1 bar, plus Z4, Z2 bar, and then finally Z3, Z3 bar, plus Z4, Z4. And this is supposed to be equal to 1, 0, 0, 1. If this is unitary, then this should be satisfied. And indeed, the equations we get is those equations 5.12, 5.12. Right? 5.152, right? Yeah, this is equal to 1, that's equal to 0, this is equal to 0, and that's equal to 1. But of course, if this is equal to 0, it's automatic, this is 0, because this is nothing else but the complex conjugate of that, right? So that was related to your question. So, so you have just one complex equation. This is just a complex conjugate of that. So those are the three equations given in 5.12. Okay. Now, and the determinant of U is Z1, Z4 minus Z2, Z3. And that's also supposed to be equal to 1 because we are looking at SU2. So determinant should be equal to 1. And now, what one does is one uses these manipulations. If all of you agree with these manipulations, then I will just proceed with the answer. If anyone has doubts about this derivation, meaning arriving at the equation Z1 equal to Z4 bar and Z3 equal to minus Z2 bar, if any of you have any doubts about that, I will go through it. No? So everyone is okay with that? So then I will just assume that this has been done. So at the end, at that manipulation, what you find is Z1 equal to Z4 bar and Z2 or Z3 equal to minus Z2 bar. Still, it's not complete. I still have to check whether it satisfies all the equations. So let's just substitute that to check if everything is okay or not. So first of all, if Z3, so let's look at each of these equations. So Z1, Z1 bar plus Z2, Z2 bar. Okay, that is one equation. That it doesn't say much about it. And then you have, let's say, Z1, Z3 bar plus Z2, Z4 bar. Let's just check that. So what I will do is I will remove, substitute for Z4 and Z3, Z4 and Z3 in terms of Z1 and Z3. So let me write this equation other way around. Z4 bar equal to Z1. So from that we see that this is the same as Z1. So this is the same as minus Z1, Z2, Z2, correct? Because if Z3 equal to minus Z2 bar, Z3 bar is a complex conjugate of that, which is minus Z2. So it becomes minus Z1, Z2. And the other one becomes plus Z2. And Z4 bar is Z1. So this is automatically 0. Right? And of course, if this is 0, then that's also 0 because this is a complex conjugate of that. And finally, this equation, Z3, Z3 bar plus Z4, Z4 bar. What is this quantity? This is equal to 1. So let's substitute again that. So this becomes Z2, Z2, so minus Z2 bar times minus Z2, right? Because Z3 bar will be minus Z2. And then plus Z4 bar is Z1, Z4 is Z1 bar times Z1. Okay, and this is supposed to be equal to 1. But this equation is the same as that equation, right? Because minus minus cancels, so it's again the same. Z1, Z1 bar plus Z2, Z2 bar equal to 1. So both of these equations collapse to just one equation. And finally, the last one, the determinant condition, again you see it becomes, so this object, left-hand side here, so this is Z1, and Z4 bar so Z4 bar is Z1, okay, and then this one becomes minus Z2. Now there's something wrong here. No, so Z4 is Z1 bar, sorry. This is Z4, not Z4 bar. So this is Z4 bar was Z1. So Z4 is Z1 bar. And here you have a minus Z2 and Z3 is minus Z2 bar. So minus minus becomes plus and that's equal to 1. So this is again the same equation. So all of these four different equations, after having used this information, which is a consequence of all these four equations, gives rise to just one extra equation, which is that equation. So this summarizes the solution, right? This completely defines the solution. And then we understood what is the interpretation of this. Geometrically, this has a very nice meaning, and that is obtained by writing Z1 as x1 plus I x2, and Z2 as x3 plus I x4. Then this equation is nothing else but x1 squared plus x2 squared plus x3 squared plus x4 squared equal to 1. This is quite good, very beautiful equation. Because it is saying that the parameter space, I mean the SU2 group is in fact, as a space, as a topological space, it is nothing else but S3, the three-dimensional sphere. And this is just a generalization of what you already know. Like one-dimensional sphere is nothing else but the circle. And how do you define the circle? You take a plane and draw a circle around the origin. Let's say origin is at 0, 0, at the origin. Then the circle definition equation of the circle would be simply, so S1 would be given by x1 squared plus x2 squared equal to 1. Let's say radius 1. I take radius equal to 1. So S1 is defined by this equation. So you take a plane and this is the origin and say this is x1 and this is x2. And then you are saying that let us look at all the points in this plane which satisfy this equation. Well, all those points will satisfy this equation, just give you this circle of unit radius. Okay. So that's the circle. S2, again, you can visualize it in the mind. It's not possible to draw it on the blackboard because blackboard is two-dimensional. But in the mind, you can visualize it. So what you now do is to look at the three-dimensional space, x1, x2, and x3. So a three-dimensional space. And you say that I will take all the points which satisfy this condition. x1 squared plus x2 squared plus x3 squared equal to 1. Okay? And now, what are the set of all those points in the three-dimensional space which satisfies this equation? That is exactly the sphere, not surface of the sphere of unit radius. Now this is a generalization of that. We cannot even visualize it because now we are in 4-dimensional. We are not, our brain is not capable of visualizing this. No. However, mathematically it makes perfect sense. So this is that's why this space is called S3. In general, Sn in general, Sn, if I take Sn, how is it defined? It's defined by going to an n+1 dimensional space. So the coordinates are x1, x2, all the way to xn+1. So these are the n+1 orthogonal directions, coordinates. And then you define the Sn as saying that this is a set of all points which satisfies this condition. So that will be the Sn sphere of unit radius. Okay. Of course, you can change the radius with some any radius r square. So that will be the Sn with radius r. But here the radius is 1. I mean, in this example, in the SU2 case, the radius is 1. So it's S3. It's a beautiful space, very nice, smooth space.
Professor.
Yeah.
Yeah, it seems to me that SU2 can be mapped into a quaternion. So, by any chance, are quaternions and SU2 are isomorphic to each other? I mean, to unify this?
Yeah. You can write it as a quaternion. I mean, quaternions are basically expanded in terms of the sigma matrices, the polymatrices.
Oh.
Yeah.
Oh.
Polymatrix and identity. So that is how you expand. Because quaternion has 4 real numbers inside, no? So you just write it as, say, x mu sigma mu, where sigma 0 you define, or sigma 4 you call it as identity. And other ones are I sigma 1, I sigma 2, I sigma 3. Yeah, quaternions are like that. Yeah. Good. So now, yeah, what was, now what happens, you see, I mean, you guys see in this derivation, the way at least it's derived in the notes is very crucially dependent on this equation, the determinant equation, right? In order to get these equations, basically what one did was one took this equation, multiplied by Z4 bar or maybe Z1 or something, and then use the other equations to simplify, and then we found that these were the 2 conditions. But this played an important role, right? But this was coming from the restriction that it is SU2. What about U2? I mean, what can you say about U2? But U2, I mean, once you know SU2, you can immediately construct the U2, because you can just take any of this SU2 matrix, so SU2 matrix here, which satisfies this condition. And so if I take a SU2 matrix, Z3 is Z2 bar, and Z3 is minus Z2 bar, and Z4 is Z1 bar. So take this SU2, which satisfies this equation, Z1 bar plus Z2 bar equal to 1. Okay. Now, given such a matrix, you can easily construct an U2 matrix by just multiplying this whole thing by a phase, any phase. No? Why? Because multiplying by phase, it doesn't, that's a number. Multiplying, what does it mean multiplying this? Multiplying a matrix means you multiply this, every element of this matrix by that number, right? That's what it means, no? So then what will happen? I mean, if U, so let's say if U is mapped to, let's say, e to the I theta times U, so you take this is a new U. So U is multiplied by e to the I theta, this is the new U. Then U dagger is e to the minus I theta, because I have to take the complex conjugate, and then U dagger, right? So now you see that the new guys also, this is the inverse of that, because inverse of this guy is precisely the U dagger times the inverse of this number. This is a number. Okay. So this immediately gives you a U2 matrix. And why? Because now its determinant is not equal to 1, because the determinant of this guy will be, so dit u will be now e to the power of I theta square, no? Times dit u. Because when you multiply e to the I theta, so what does it mean? I am multiplying e to the I theta to every element here, right? Now when you take determinant, it will become e to the I theta z1 times e to the I theta z1 bar, which means e to the 2 I theta z1 z1 bar. Same thing here, this becomes plus z2 z2 bar times e to the 2 I theta. Okay. So determinant is simply the original determinant times e to the 2 I theta. Okay. So dit u initially was 1. So what we are saying is that now after multiplying by e to the I theta is no longer SU2 matrix, but it is a U2 matrix whose determinant is e to the 2 I theta. So even though we have used this equation crucially to get all this, but once we have obtained SU2 matrix, to get U2 matrix is trivial. You just multiply it by a face, and that gives you the general U2 matrix. That's one thing. And another thing I would like to point out, okay, this I think it was one of the exercises to check that this SU2, I mean, let me just write it here. Z3 was Z2 bar, minus Z2 bar, and Z4 was Z1 bar. So this is my matrix, SU2 matrix. It's a completely general SU2 matrix. Meaning every SU2 matrix can be expressed in this form, where it has to be of this form. That is now you see that this one of the questions, I think it was the exercise. Let me see. Yeah, exercise 5.2, which is to show that SU2 is non-abelian. Right? You remember SO2 turned out to be abelian, right? But here one can see that SU2 is non-abelian. Okay? That's easy to see. I mean, so this is an exercise. But there is one interesting element here. Okay, what is the identity of this matrix of this SU2? Identity is simply the identity matrix 1 0 0 1. Right? Because I mean, this is certainly, you just choose Z1 equal to 1 and Z2 equal to 0. You just get that, right? So this is certainly an element. That's identity matrix, and any other U matrix you multiply to this, it's going to give you back again U, right? That's a definition of identity. And inverse also fine, because U inverse is nothing else but U dagger, right? Because U dagger, U is identity. So U dagger is the inverse of U. So this is also fine. So certainly there is this element which will commute with everything, right? Because this identity. So this is, let's call it E. So E times U, of course, is equal to U times E, by definition, right? In fact, this is equal to U. So E commutes with every element of SU2, right? That is true. The question you can ask is there another element which also commutes with all the elements, right? And the answer is yes, because I mean, for this to be true, I mean, any element which is proportional to identity, which is some number times identity, will also satisfy this equation, right? So suppose I take let's say there is some, I multiply by x, xe, u equal to u xe. X is a number. This is obviously true, right? Question is, however, is there any value of x for which xe also belongs to SU2? Okay? And the answer is yes. I can choose x equal to -1. So -1 also belongs to SU2. Okay. That you can choose, see, because if I can just choose Z1 equal to -1, right? Z1 bar is against -1 here, and then Z2 is 0. So this is also an element of SU2. In fact, this is a very general property. I mean, what we did here was SU2, but you see, you can see also for SUN. SUN, if I take SUN, so this is an n by n matrix, right? So n rows here and n columns here. Okay. And certainly the identity will be simply the one n cross n matrix. That's an identity, right? Because whatever, I mean, we are not solving these equations to determine what are the most general matrix of SUN, but whatever it is, it's some matrix which is unitary and determinant equal to 1. Okay? So let's call this matrix some U, some matrix M. So M dagger M equal to M is our n cross n matrix, M dagger is also n cross n matrix, and we have the requirement, this is identity, and determinant of n equal to 1. Okay, this is a condition. So all of those, whatever matrices you find, the solutions you find from this equation, whatever that matrix is, it is going to commute with this E. So this is going to be the identity of the SUN, because clearly this is of course unitary and it's also determinant equal to 1, right? So this certainly commutes with everything in the SUN. But now the question you can ask is, are there other elements? Is there any other element, just like in SU2 we found there's another element here? Is there another element of SUN which again commutes with every other element of SUN? Okay? And the answer is again the same thing. If there's an element which is x times identity, okay, then that's also going to commute when x is a number. But we have a condition. Okay, first of all, this is so there is a condition that this, first of all, it must be unitary. Okay, so that means x better be only a pure face. Yeah, x must be only a pure face, because what is the dagger of this guy? Dagger of this guy is x bar times identity, and I want to take the product of these two. Is going to be identity times x bar, x mod square, right? This that better be equal to 1, otherwise it will not be unitary. That means x has to be a face. Okay, so x is of the form e to the power of I theta, for the theta of some theta. Theta could be arbitrary at this stage. But now we have a condition. We have the condition that also determinant, because we are talking about SUN, not UN. We are talking about SUN. Huh? So the determinant of this matrix must be 1. Okay. So what's the determinant of x times identity, n cross n? Well, this is going to be x to the power of n times 1, right? Because after all, what does it mean, x times identity? It is just putting x in the diagonal, right? And everything else 0. That is what is x times identity. This guy is that, right? X times identity. So you take determinant, it becomes x product of that, which is x to the n. Okay? So you get that. So the condition that the determinant equal to 1 implies, so this equal to 1 implies that x to the n equal to 1. Okay? But x we already saw is e to the I theta. So this means, this implies that e to the power of I n theta should be equal to 1. Okay? So we come to this conclusion that so theta, what possible values theta can take? Theta can take 2 pi by n, 2 pi divided by n, because e to the 2 pi I is 1, right? E to the 2 pi I is 1. So therefore, the possible values of theta are, okay, 0, which gives you the original identity matrix, then 2 pi I over n, 2 pi over n, sorry, because I is already there inside, 2 pi times 2 over n, 2 pi times 3 over n, all the way up to 2 pi n minus 1 over n. Okay. These are all possible values. Why I stopped here? Because if I look at the next one, which is 2 pi n over n, that is just 2 pi, right? The next one, next one would have been would be 2 pi n over n, right? I and just increasing the numbers, 1, 2, 3, n minus 1, and n. But that number, 2 pi n over n is 2 pi, but if theta is 2 pi, it's just 1. So you come back here, right? So this is not some new element. This is the same element. This is Zn. This is what I was calling Zn. No? This is, if you look at this thing, so what we are saying is that these elements are simply e to the power of I, theta, 2 pi, r over n, where r goes from, this x is that, where r is going from 0 up to n. So this is just Zn phases, huh? And so what we see is that actually there are n elements in the SUN which commute with every other element of the group, So which means, in fact, there is a special name for it. That's a subgroup, and there is a special name for it. When the center of the group, this is what is called the center of the group. So center of the group is a subgroup of the original group which commutes with every element of every other element of the group. That's the center of the group. So we come to the conclusion that SUN, the center, is the Zn, whereas for SU2, the center is Z2, which consists of this element and the usual identity. These two elements corresponds to the center of SU2, and they commute with it. We will see that this center will play an important role when we talk about the representations. The representations of it. And also it will play a role when we talk about SO3. I mean, when we try to look for the relation between SO3 and SO2. Fine. Now let's go to the infinitesimal generators. Any question here before I erase this part? Okay, no question? Okay, now we go to the infinitesimal generator, which we used. I mean, that thing, what does it mean, infinitesimal generators? Those are the ones which are just close, elements which are very close to the identity. No? So we concentrate on the generators, which we discuss in discussing the conserved quantities, Noether theorem. No? So we'll look at the generators now. Okay, so let's let's go back here. Here's Z1, Z2 minus Z2 bar, and Z1 bar. So this was an arbitrary element of the SUT. So we want to write the identity is 1, 0, 0, 1. This is the identity of the SUT. So we want to look at Z1, Z2, etc., which give you some matrix which is very close to identity. Okay. So what does it mean here? So I can write this now. So near the identity. So we are assuming that this is very, very close to the identity, which means these are all very small numbers. And this is close to 1. So this is 1 plus some small number, 1 plus some small number, and Z2 is very close to 0, very small number. So let's write U is equal to identity matrix. Okay, either let me call it identity matrix, I2, 2 by 2 identity matrix, plus some small infinitesimal parameter. This epsilon is like what you do when you study differential calculus, no? The concept of derivative. You take epsilon limit, epsilon goes to 0 limit. So that's exactly what we are doing here. So epsilon times some matrix n plus order epsilon square. Okay. So there will be some expansion. 1 plus epsilon square, epsilon cube, and so on and so forth. But we will ignore all the higher order terms. Okay. So what is U dagger? U dagger is going to be this dagger of this I2 is I2 plus epsilon. Epsilon I'm taking to be a real number, real small number, very, very small, infinitesimal number. Infinitesimal number. Okay. So this will become epsilon is real, so nothing happens when I take the dagger, and it's a number, so transpose doesn't matter. And here you just get m dagger plus again order epsilon square. I mean, this order epsilon square terms will be different from those order epsilon square, but whatever it is, order epsilon square. And we are not interested in that. We'll just anyway throw them away. Okay. Now, the unitarity condition, what does it say? U dagger is equal to identity. Right? That is a unitarity condition. So, let's just plug this in here. So, I'm going to get this plus times that. So identity plus epsilon n plus order epsilon square. When I say order epsilon square, of course the matrix is understood that it's just order epsilon square, but it's of course the n 2 by 2 matrix. These are all 2 by 2 matrices. And here identity plus epsilon n dagger plus order epsilon square. Let's open it up. So identity times identity is 1 identity. Okay, this is I2, again this is I2. Plus order epsilon terms comes from 2 possibilities. This can multiply that, or that can multiply that, right? The 2 possible terms. So you get here epsilon times m plus m dagger. And then everything is order epsilon square. Because this multiplying that is already epsilon square. That multiplying with this is again order epsilon square. And finally, if you look at this term, this is epsilon m dagger, which is also epsilon square order. Epsilon square times m dagger, right? So everything else is order epsilon square. So only first order term in epsilon is m plus m dagger. And this is supposed to be equal to identity. Well, this is already, so this was identity. So this is already cancelled that. So what we are seeing is that to order epsilon, this better be 0. 0 matrix, right? 0 as a matrix. So that gives you a condition. This implies m dagger equal to minus m. So another way to say is that m is anti-Hermitian. Okay, Hermitian and anti-Hermitian depends on how you expand. Here I took epsilon to be real, right? You could have also taken it to be I times epsilon. No? You could have written here. If you had taken I here, then when you take the dagger, it will become minus I. Okay? So here it would be I, there would be minus I, and here you will get I, m minus m dagger. Okay? So in that case, requiring this equal to 0 means m dagger is Hermitian. But that's not surprising, because if I multiply by I, see what here this statement is saying n is anti-Hermitian. If I had multiplied by I, then I times m is automatically Hermitian, right? So this is not surprising. And in fact, that could be one of the confusion, because in many literature, in many books and papers that you will read, sometimes some authors write without an I here, some authors write with the I, okay? So in the two, but that's just different convention. Nothing, there's no difference. Huh? It's just that in one case, when there's no I, then that m has to be anti-Hermitian. If you see some paper where there is an I there, that means then this m must be Hermitian. Okay, so this is this should not. I mean, don't let it confuse you, because in different literature you will see both the notations. Physicists usually like to deal with the Hermitian matrices. Okay, physicists. So they put an I. Physicists. Yeah? Whereas mathematicians prefer to deal with the anti-Hermitian matrices. So they do not put an I there. But anyway, it's you should just be able to go from one language to another language without any problem. All right. So this is anti-Hermitian. So what is the most general? You see, unlike solving this equation, the equation which we were solving, u dagger u equal to identity. This equation was difficult. I mean, although for 2 by 2 it was turned out to be much easy, very easy, right? You could actually solve it almost completely. No? But in general, you see this equation is a quadratic equation in the unknown quantities, right? And there are many, if you take an n by n matrix, there are n square unknown complex numbers here, no? And Unitary also has this n square complex numbers. So this whole thing is going to be n square equations involving n square unknown quantities, n square quadratic equations. So it's quite a difficult set of equations to solve. But this equation is trivial to solve because it's a linear equation. You see, unknown quantities are this matrix M. And dagger is of course given in terms of those unknown quantity. So this is completely linear equation. So it is trivial to solve this equation. Right? So for example, in our case, we are looking at 2 by 2 matrices, and you can have you people seen? I mean, have you all seen something called polymatrices? Sometime polymatrices. Okay, if not, okay, let me. Pauli matrices. Sigma 1, sigma 2, sigma 3. Huh?
Yeah.
Yeah. So those are yeah. So exactly. So let's write down what is sigma matrices. So sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I 0. And sigma 3 is 1, 0, 0 minus. Okay. Now, all of these have a very interesting property. See, these are all Hermitian matrices. All of these are Hermitian matrices. Hermitian matrices. And also they are traces. They are traces. Trace of these matrices is 0. Trace of these matrices is also 0. Okay? You can of course add to this again the identity also, 1, 0, 0, 1. That will be again Hermitian, but its trace is not 0. But the trace of this is not 0. The trace of the first 3 are all 0. And the trace of this is not 0. I don't know, this is identity. Unit matrix. Now this, so at the moment what we are seeing this anti-Hermitian, right? These are all 2 by 2 matrices which are anti-Hermitian. So far I didn't discuss whether, we don't know whether the trace is 0 or trace is not 0. We don't know yet. But it will turn out, I will shortly discuss that the trace has to be 0. But for the moment already, we see that, because I have not imposed determinant condition, I have only imposed the unitarity condition. I have to still impose the determinant condition, the determinant equal to 1. But at the moment already we see that the most general solution of this equation is to write, can be expressed, most general solution can be expressed as some I, because those are all Hermitian. So I need to multiply by I. No? I times, let's say, I don't know, let me use the same symbol. Same notation. Okay, yeah, let's write like that. So I, CA, sigma A, where CA are real, right? Because you see, sigma A are Hermitian that we saw. So any real number times that matrix is also going to be Hermitian. But what we want is anti-Hermitian. So I just multiply by I. Okay? That plus possibly this term, plus I times, let's say some C0 times the identity matrix. So this A goes from 1 to 3. So there is a summation A going from 1 to 3. This is the most general solution to this equation. There can be only 4 solutions, right? Because after all, these are 2 by 2 matrices, right? Let's just try to do this. Let's suppose, let's write n equal to, let me not use the same z. What can I use? Let's call it w. W1, W2, W3, W4. This is the most general matrix, M. Is complex matrix. These are all complex matrices, and these are complex numbers. This is the most general matrix. Now I want to impose this condition. So what is M dagger? M dagger is W1 bar, W3 bar, W2 bar, and W4. Bar meaning complex conjugate, right? Now we want to impose this condition. So this is equal to that. This is equal to minus of that. Okay. So term by term it should be agreeing. So what is M dagger? So let's look at M dagger plus M. Right? Because this must be 0. If I take it to the other side, M dagger plus M is 0. So what is M dagger plus M? That's nothing else but W1 plus W1 bar, W2 plus W3 bar, and W3 plus W2 bar, and W4 plus W4 bar. Right? And this is supposed to be equal to 0. I mean 0, 0, 0, 0. 0 as a matrix. Okay, so what does it mean then? Let's try to see. So these are all, we said complex numbers, right? So for what we are saying, W1 plus W1 bar is 0. That means this is a pure imaginary. W1 is a pure imaginary number, right? So W1 is some I times x1. Let's say. Okay? That will satisfy this equation. Similarly, W4 is equal to I times x4. x4 is real, so x1, x4 are real. Okay. Now let's look at this equation. So let's write W2 is equal to, let's say, general y2 plus I. I'm running out of the symbols here. Let's call it x2 plus I y2, and W3 equal to x3 plus I y3. Where x2, x3, y2, y3 are all real. Then this equation, let's substitute that here. So W2 plus W3 bar is equal to x2 plus x3 plus I y2 minus y3. Because complex conjugation will flip the sign of this. And W3 plus W2 bar is equal to, again, x2 plus x3 minus I y2 minus y3. Okay. Well, if this is 0, then that has to be 0 because it's complex conjugate. So then we have two conditions, x2 plus x3 equal to 0 and y2 equal to y3. Okay. So let's take the two, so W2, so x2 is pure imaginary. Sorry, it's x2 plus x3 is 0, x3 is minus x2. So what we are saying is that W2, so let's say I write W2 equal to x2 plus I y2, then W3 must be x3 equal to minus x2, so it's minus x2, and y3 equal to y2, so plus I y2. Okay, this is the most general matrix. So let's write down this matrix explicitly. No, I don't want to erase that. Let me see here. So I write this matrix. What we have is, so I write M. M is W1. W1 most general is I. So let me take out the I, or let me keep it here. I x1. Okay. W2 is x2 plus I y2. x2 plus I y2. And W3 is x3 plus I y3, which is the same as minus x2 plus I y2. And finally, W4 is I x4. This can be written as I times x1, x4. In fact, let me write it like this. Okay, I will do it in two steps here. I x1, x4. Okay. Take the diagonal part, and now look at the off diagonal parts. So here I y2 times 0, 1, 1, 0. Okay. and take the coefficient of x2, and in fact let's take ix2. So ix2, that's the same as 0 minus I0, right? Because you see, you multiply that here. Ix2 times minus I is plus x2, that is plus x2 there. And ix2 times I is minus x2, which is that. Okay? So I just rewritten this as a sum of these matrices. And furthermore, I can also split this in the following way. Write this quantity so as x1 plus x2 plus x1 minus x2 divided by 2, 0, 0. And this one is x1 plus x2, sorry, this is x4, no, x1 plus x4, sorry, x4, x4. And here I write it as x1 plus x4 minus x1 minus x4 divided by 2. So what I've done, I've just rewritten the same thing in a slightly more convenient way. If you add this up, indeed x4 cancels, you get 2x1, so that's x1. 2x1 by 2. Here, on the other hand, x1 cancels, x4 adds up, and you get that. It's just a way of rewriting it, convenient way of rewriting it. Because now, I can write this as I times x1 plus x4 by 2 times what? Times the identity matrix, and I times x1 minus x4 by 2 times the polymatrix sigma 3, because this is simply 0, this is 1, 0, 0, minus 1, because there is a coefficient minus. And these are sigma 1 and sigma 2. So indeed you see that you can expand the most general solution for this condition m dagger plus m equal to 0 as a linear combination of these four matrices with the I. Okay? Because these are Hermitian, and what you want is anti-Hermitian. Okay? So the most general solution for M is a linear combination of these four matrices with the imaginary coefficients. Okay? That's what we are seeing here. That's why, I mean, the solution of this kind of equations is very complicated, because these are nonlinear equations. Whereas solutions of this type, where m dagger plus m equal to 0, these are linear equations. You can solve it very, very easily. Okay, now let's finally go to the, we still, as I said, we have not imposed the condition that the determinant equal to 1. Okay? So at this point, what we are describing is a UN, a U2, not SU2, because we have not imposed the determinant condition. We have only imposed the unitarity condition. And unitarity condition allows you these four, so unitarity condition basically says that any n, which is unitary, can be expanded as some I times, say, x1 times identity plus I, or let me write x, xa times sigma a plus I times identity matrix, some y times identity matrix. Okay, where xa and y are real. This a goes from 1 to 3. So this is the most general Hermitian matrix, anti-Hermitian matrix, where xa and y are real. Okay. Now let's go to the determinant condition. This is slightly more tricky, but there's a trick, and this trick is used in many places. In fact, you will also see it in the quantum field theory courses and so on, this particular trick. The thing is the statement, okay, I will just first write the statement. So what did we do? We said the U was identity plus epsilon plus epsilon times m plus our epsilon square. Right? That's what we said. Now the condition is on determinant of U. We have the condition determinant of U equal to 1. Okay? Then the statement is that if you are interested, I mean in general, U has an expansion, right? So you can expand it, open it up. If I set all the epsilon equal to 0, then identity, determinant of 1 is of course 1. That is of course satisfied, right? But now if I put 1 plus epsilon m, the determinant in general will not be equal to 1, right? I mean, so there will be first order corrections in epsilon. So in general it will have an expansion plus epsilon times something, plus epsilon squared times something, and so on, right? If I just take an arbitrary u of this type, right? That is what it's going to be. So the statement is that this term, in fact, is equal to, this coefficient is in fact nothing else but the trace of it. Okay, and the one way to...
I have a question, Professor.
Yeah.
Isn't epsilon supposed to be the continuous parameters of U?
So, sorry, repeat that again? Yeah, it will depend on the parameters in U, yeah. Is that determinant? I mean, so this, like, so in general what it will be? So we are writing U equal to identity plus, as we said, epsilon times some matrix here, I don't know, M11, M12, M21, M22, okay? Plus order epsilon squared times another matrix, epsilon cubed times another matrix, and so on and so forth. These are all inside these coefficients, right? There's a Taylor expansion, essentially, of that, right? Now I compute determinant. So this determinant is clearly a complicated mess, right? And in fact, let's write it down. So here, so let me put everything together. So 1 plus epsilon m11 plus, so what shall I call it? Let's define something else. P11, P12, P21, P22, etc. and so on. So let me just write explicitly up to epsilon square plus epsilon square P1. Right? That's in the 1, 1 coefficient. 1, 1 term. The 1, 2 term will be 0 because identity is diagonal. So we write 1, 0, 0, 1. Okay. Then it will start off with epsilon m11, m12, sorry, plus epsilon square p12 plus higher orders. And here it will be epsilon m21 plus epsilon square p21 plus dot dot dot. And finally, this one here, I did 1 here. So you start with a 1 plus epsilon m21, m22, sorry, m22 plus epsilon square p22, and so on. Okay. This is what it is, right? Now, the determinant we can compute. Let's write down explicitly. This we can do because it's 2 by 2 matrix. You can imagine now if it's n by n matrix, it's going to be a mess to do it, right? Quite difficult to do. That is why I will introduce another trick. And that trick is useful because that trick can be used even when the matrix is infinite dimensional, infinite by infinite matrix, which is used extensively in the path integrals. In the quantum field theory course you will study in the next semester. Okay. So let's just see. Let's multiply it out explicitly. So I will keep only up to linear term in epsilon. So I will, okay, let me keep that for a moment. So when I put a determinant, so it is this times that minus that times that, right? That's the determinant. So the determinant of this is 1 plus epsilon m11 plus epsilon square p11 plus dot 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 times 1 plus epsilon m22 plus epsilon square p22 plus dot 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 minus, I have to take the product of this with that. So that this one is epsilon m12 plus epsilon square p12 dot 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 times epsilon m21 plus epsilon square p21 plus dot dot. And this whole thing is equal to 1. That's what we have our conditions, right? Okay. Okay, for the moment, let's forget. Okay, we want this to be equal to 1. Okay, leave that. I mean, that really imposes a condition. So let's just compute it. Let's compute and expand again in powers of series epsilon. So first of all, let's look at the epsilon to the 0 term. Notice that this term, which is the product of the off-diagonal terms, this is at least epsilon square order, you see, because there is already an epsilon here. You can take out an epsilon altogether. So then if I take out an epsilon, this becomes 1, that becomes that. And here also the epsilon is a common factor, so I can take out there, right? So there is already epsilon squared. So this term will start off as epsilon squared times m12, m21. And then higher order is an epsilon, so epsilon cube order. Right? That is this term. What about that term? That, you see, we are not interested in epsilon squared term at all. So in fact, the off-diagonal term doesn't contribute at all to this. Right? Only thing which contributes is this one. Let's open that and see what are the, first of all, there is a term 1, which is 1 times 1. Okay, that's that. Now let's look at the order epsilon term. Order epsilon will come from this times that and this times that. So that's epsilon times m11 plus m22. Okay. And then order epsilon square. Epsilon square will come from several things. I mean, you have a you'll have P11, I mean, this times that, that times that, and this times this. So P11 plus P22 plus M11, M22. And higher orders, absolutely, because there's a dot, dot, dots here, so there are dot, dot, dots. So this is the expression. So this minus that, minus this. Okay. Now, we want this to be equal to 1. In fact, before even wanting. So what do we find? The answer, final answer is 1 plus epsilon times m11 plus m22. But that's nothing else but the trace of m. Trace of this matrix M, right? Because this M, we wrote it as m11, m12, m21, m22. So the trace of this matrix M, this is what we wrote here, right? This matrix M is, in fact, m11 plus m22, trace. Trace is the sum of the diagonal terms, right? So this is the trace of M. And then order epsilon square. Okay? Because everything else order epsilon. Here, everything else order epsilon square. So since we have since we are looking only up to the first order term in epsilon, for SU2, since we require the determinant should be equal to 1, then this must be vanishing. Okay? We want to be sensitive up to epsilon. Right? We want to make sure that conditions satisfied up to order epsilon. So up to order epsilon, this condition says that trace of M must be equal to 0. That's the condition. Is that clear? Any question on that? I mean, this was easy because it was just 2 by 2 matrix. We could explicitly calculate it. Although one thing you can see immediately, right? I mean, even if it is even if it is a higher dimensional matrix, you can see that this should be true in general. Why? Because so let's say I have an n by n matrix, and I start expanding near the identity. So identity plus order epsilon plus order epsilon square and so on and so forth. So let's look at the order. So identity means you already have the diagonal elements are all 1, start with. Then you have order epsilon m11, epsilon m22, plus order epsilon mnn, mnn. Okay, this is an n by n matrix. Okay. What about the off-diagonal terms? Off-diagonal term would be already epsilon m12, here epsilon m21, epsilon m13, epsilon m31. Here it will be epsilon m23, epsilon m32, etc. And so on. Now the important point is that when I compute the determinant, this is when I compute determinant, I say open the brackets, open individual terms. So first of all, there is a product of all this diagonal. Okay, there's a product of diagonals. But now look at the off-diagonal terms, how it will come. if I start from here, this is necessarily going to multiply one of these extra pieces in the off diagonal, right? Like in the, say if I do a 3 by 3 matrix, if I open up the determinant like that. So this times that, minus this times that, correct? But that times that's already epsilon square term. Okay? Because you have two off diagonal terms are multiplying in this term. So whenever there are two off diagonal terms that are multiplying, all those terms are already epsilon square order, so we don't need to worry about it. Okay? So, in fact, you can see there is no term where if you pick one off diagonal term, it comes at, there is no term in the determinant where you have all the diagonal terms except one, and that last one being the off diagonal term. That's not possible, right? Because for example, so here, is that clear? I mean, so this times determinant of that. That means the determinant of that is this times this minus this times this. So there are at least two off diagonal terms here, right? The one which is this times that is okay. That is there are no off diagonal terms here. But here this term has two off diagonal terms. Now let's look at, we are opening up like that. Let's look at this here. So there will be two terms. This times that, and this times that, right? This times that has two off diagonal terms. This times that has actually three off diagonal terms. Right? So that will be epsilon cube order. Right? Same thing happens here. If you start from here, then there is this times the determinant of that, which will be this times that, which is again three off diagonal terms, so it's epsilon cube order, and then this times that. That is 2 epsilon square order. So there is no way. I mean, if you are only interested in up to first order in epsilon, then the determinant, you can just equally say that the determinant is only the product of diagonals. You see. So we are saying, since we are only interested in up to order epsilon term, not epsilon square and so on. The determinant of this matrix is the same as just taking the product of diagonals. So 1 plus epsilon m11 times 1 plus epsilon m22 all the way up to 1 plus epsilon mn. Okay. Now open this up. So first term is all 1, 1, 1, 1, 1. So that's that. Now again, I'm only interested in order epsilon. So what does it mean? If I pick up epsilon m1 from here, then I should necessarily pick 1 from each of the other factors, right? If I pick up epsilon m22, then I should take 1 from all the other factors, and so on, right? So you will have the epsilon term will be simply m11 plus m22 plus m33 all the way up to m. And that's nothing else but the trace of m. Trace means the sum over the diagonals. No? So epsilon times the trace of m. So this is the general statement. That is the first order term in the determinant expansion is epsilon times trace of m. Then therefore, the determinant of u equal to one condition, determinant of u equal to one condition implies up to order epsilon. What it implies on m is a trace of m equal to 0. That's the main condition. Now let me just try to show this in a slightly different way, which will be very useful, as I said, in the quantum field theory course. So the statement is, let's say, suppose I have some matrix A. So let's say there's some square matrix, or it could be even operator, could be even differential operator. Could be, actually, in quantum field theory, you will come across differential operators, and you want to compute determinants of them. So, when you say the determinant of this operator is nothing else but the product of the eigenvalues. So, if you try to write down the eigenvalue equation, A psi equal to lambda psi. In general, there will be many different eigenfunctions, and eigenvalues. Okay. Then this A is nothing else but the product over all the eigenvalues. Okay. This, I don't know if you have studied in linear algebra. For example, if you have Hermitian matrices, or Hermitian or unitary matrices and so on, then you can find, if you can diagonalize the operator by making similarity transformations, by changing the basis, so that diagonal elements are all eigenvalues of the operators. Since when you do the similarity transformation, the determinant doesn't change, okay, then the determinant of the original operator, original matrix, is the same as a product of eigenvalues. So that's the statement. So this is the product of all the eigenvalues. So determinant is the product of all eigenvalues of the operator. Okay. Where eigenvalues are defined by this equation, that A acting on some the vector is equal to some number times the same vector. That's the eigenvalue equation. Then now what we are doing, I can rewrite this as exponential of, so product of the exponential of log lambda I, right? So there is a product over that. This is nothing. I mean, exponential of log of something is the same as original thing, right? Exponential and log are inverse operations. So this is nothing. I mean, this is. But now, when I take the product, this is exponential. This is the same as exponential of some I log lambda I. Okay? Some I log lambda I. But this is the same. See, some I. So sum becomes a trace, right? Sum is a trace, whereas products were determinants. So when I take the sum, this is the same as exponential of trace log A. Now, what is a log A? This is a bit mysterious, right? I mean, what is a log of a matrix? A is a matrix. So what's the log of A if a matrix? Well, it's by, this is a way of, this is a notation. This is a way of saying that log A is that matrix whose eigenvalues are log lambda I. Okay, this is we don't need more than that. Okay. This is just that. Okay, so now let's suppose that we want to look at a small change, epsilon expansion, right? So therefore, let's write A is equal to some identity. I mean, A is the same as, we are thinking of U, right? So A is the same as U here, identity, plus some epsilon times some M, plus higher order epsilon, plus higher epsilon square. Then, what is this? The determinant of A, we are saying, is nothing else but exponential of trace of log 1 plus epsilon f plus r. Now, log of 1 plus some small quantity is what? Is that small quantity, right? So this guy, I mean, log of 1 plus log of identity plus epsilon and plus higher order terms, epsilon square, is the same as the epsilon m plus higher order epsilon. this I'm just using the fact that log of 1 plus x starts off as x, if x is small, and then higher order is x, order x squared. But first term is x. Log of 1 is 0, right? So it starts from that. So you find that this quantity then becomes exponential of trace epsilon n. Epsilon is a number, I can take it out, plus high order epsilon square. And now I can expand exponential, so it will start off as 1, 1, and then you'll get the trace of epsilon times trace of it, plus high orders in epsilon square. So this shows that the determinant of A is 1 plus epsilon times trace of it. Have I confused you a lot with this alternative derivation? I already showed you directly in terms of matrices, right? That it's just going to be 1 plus up to order epsilon to be just a trace of it by that manipulation, right? Where we explicitly looked at the determinants, no? That whenever any off diagonal term appears, it will come with at least order epsilon square. So only the diagonal terms will appear in the determinant. But this is an alternative derivation, which is useful because particularly in quantum field theory course where A is not even expressed as a matrix, it's usually written as differential operators. But it doesn't matter, differential operator will have some again eigenvalues, and this analysis can be used there. And it's used very frequently in that context.
Professor,
Yeah.
what happens when we have an eigenvalue that is 0 in this case?
If the eigenvalue is 0, then of course a determinant of A itself is 0. Yeah. You can't, you cannot even write it as log, because, because if you want to write, so this itself is 0, right? So you cannot even take the first step, because if I want to write, apart from that situation where you have any zero eigenvalue, in which case, as you are saying, if you want to write 0 as exponential of something, then this something will be minus infinity, right? So that will not be allowed. So what happens in quantum field theory context, you are right, this is a very serious problem. So what they do always is they call it determinant prime A. Okay? What is determinant prime A? You remove the 0 mode, and then you take the product over the remaining parts. Okay? And what happens is in this case is that the 0 mode can be handled in a separate way. So you deal with it separately, and then talk about the remaining part. But yeah, indeed, it's a very important point. Yeah. So this will be really, you need to remove the 0 mode then. Okay. But at least in our case, there is no such issue, right? So let's say that there are no 0 modes, this procedure works through. When there is a 0 mode, you have to be more careful. Okay. You have to project out, and you have to look at the subspace after removing the 0 mode. Then you look at the orthogonal space to that 0 mode, and redefine a new operator there, which is related to, of course, the old operator. The way old operator acts on the space, but now you restrict that old operator to a smaller space. And there you can define this. But that's what is important. In the path integral, in the quantum field theory, what happens? These are all infinite by infinite dimensional operators. The space on which it acts is a function space. So there are infinite, that itself is infinite dimensional. Okay? So the number of eigenvalues are infinite numbers, and you have to take the product of these infinite eigenvalues. Now, if there are 0 modes, the 0 modes are typically finite numbers. Okay? There are only finite number of 0 eigenvalues. So those guys you can remove. So that subspace where there are 0 modes is a finite dimensional subspace. You can remove that, but still you are left with the infinite dimensional space, right? And in those cases, you have to deal with that. You deal with this way. Okay. Anyway, we didn't need that really, but it's already. Oh my God. Okay, what I will do, I will. It is when we complete this part. So what was the point here? You see, initially we said before imposing any condition of determinant condition, when we just impose a condition that u dagger u, u dagger was 1, and we wrote u as identity plus epsilon n plus order epsilon square. Then we saw that epsilon could be n could be expanded as I times some, let's say, what is the symbol? Okay, let me call it xa, sigma a, plus some I times say x naught, a going from 1 to 3, x naught times identity. Because as we saw, there are 4 independent Hermitian operators, 2 by 2 Hermitian operators, sigma a, the 3 polymatrices, and identity. So since M had to be Hermitian from this part, I mean this already implied that M dagger anti-Hermitian, M dagger equal to minus M, then I can always expand them in terms of this basis. This is the basis for the Hermitian operators. So I can write this any real coefficients times this basis, which is that. But then since it has to be anti-Hermitian, there's an overall I factor. Right? So I can write I times this. So this is Hermitian. So this is in fact a basis for Hermitian operator, Hermitian matrices. The basis for Hermitian, 2 by 2 Hermitian matrices. Okay. So it is not surprising that this is you can write any M as a linear combination of this. But now still we have not imposed the condition that u equal to 1. We have to impose still this condition because we are looking for SU2, not U2. So we have to impose that condition. And when you impose this condition, that condition from this all these arguments is the same. The trace of n must be equal to 0. Okay. Now trace of 1 is certainly not 0. This is a 2 by 2 identity matrix. Trace of identity is 2. Whereas we saw before, trace of all the polymatrices were 0. Right? So this means that x naught must be 0. So this condition, once you write n in that form, this condition implies that x naught is 0. Okay. So therefore the generators, the infinitesimal generators of SU2 are simply this first term. Is a linear combination of the polymatrices because x naught is 0. If you had taken u2, then it would be also x naught, because then
why x naught is 0?
Because determinant of u equal to 1. I mean, so far you see in this discussion I didn't impose determinant condition. Now I impose determinant condition, right? Because u has to be not only unitary, but determinant should be also equal to 1. So when I impose determinant of u equal to 1, then from all of this discussion, we saw that to the first order in epsilon, that condition gives you the condition on the n, that is trace of n equal to 0. Okay. Now we are saying n is, so just from this condition, we saw the unitarity condition, we saw n is that. The most general n is of this form, right? But now I take the trace of it. So what is the trace of this? Trace of this will be I, xa, and sum over a equal to 1 to 3, xa times trace of sigma a plus I times x naught trace of identity. Okay? And these are numbers. So these numbers are, the matrices have this. So but trace of sigma a are 0. If I erase that part, but remember sigma 1 was 0, 1, 1, 0. Sigma 2 was 0 minus I 0, and sigma 3 was 1, 0, 0, minus 1. So this is traceless. See, all three are traceless. So all of these guys vanish. So it doesn't matter what the values of xa are. But this is not, this trace of identity is 2. This guy is 2. Right? It's a 2 by 2 matrix, trace is 2. So it's not 0. So since our requirement is a trace of m equal to 0, that means x naught must be 0. So this must be 0. This comes from the determinant condition. So that's what it is. Now you see, of course, you should have guessed anyway that the 4 real parameters is too much, right? Because you know the SU2 group involves only 3 parameters. It is the S3. We already saw the S3, which is 3-dimensional, right? There are 3 parameters. So it cannot be that there should be 3. There are 3 parameters here, right? And that was because we were not imposing the determinant condition. Once you impose that, then you see this goes out, and there are 3 parameters. And okay, now unfortunately it is true. I will now next what I will do is to look at the geometric interpretation of these generators, and we'll identify with the tangent space around the identity. You remember SU2 space was S3. We saw it as S3, right? Geometrically that space was S3. Identity is one particular point in that space. Okay, the identity element is just one particular point there. And when you're looking at the neighborhood of the identity, so which means nearby points, so what this generator is giving is actually the tangent space at the identity. So we will discuss that and then move on to SO3. And then we'll see the relation between SU2 and SO3. Okay? It will, yeah. It will turn out that there is it's not exactly, I mean, like unlike U1 and SO2, we saw that SO2R is the same as U1, right? That will not be the case here, but very close to the same. We will see that SU2 and SO3R will be very close to it. I mean, will be almost the same, but there are some subtle differences there. Okay, let's stop here because if I start with the next topic, it will at least take half an hour. So I think I better stop there. Any questions?
I have a question.
Yeah.
In SU2, when we have a general matrix, it has the Z1 and Z2. At Z1 was X1, X2, or so. Yeah. For example, then we have in S2 we have 4 parameters, but since we have the determinant is equal to 1, we have 4 parameters and 1 extension, or 2 parameters in general. I mean, because of that we have 2 parameters, no?
So I couldn't hear very clearly. So again, repeat that again.
We have 4 parameters and 1 restriction, so that's why we have 2 parameters. No?
Yeah, I mean, yeah. Yeah, there was a determinant condition which gave yeah, I mean, as I mentioned that, you see, the way we solved that equation for SU2, we were already using the determinant condition. Remember the way we proceeded. But once you have found the determinant condition, then you can, using the determinant condition, you found that the general form of the SU2 matrix, right? Z1, Z2, with the Z1 mod square plus Z2 mod square defining this S3. You did that. But then, suppose you want to go back to the U2, the full U2, right?
Yeah.
Then, I remember the beginning, before this we started discussing, I mentioned to you that you can write down a U2 always as some e to the I theta times the SU2 element, right? So that means, SU2 itself, yeah, in fact, you can see this actually. So in general, for a U2, we are saying, we are saying that U2, for the U2 group, if I take a U, that can be written, I don't know, let's call it U hat. So U hat is an element of U2. Right? So U hat belongs to U2. Then I can always write U hat as some phase, okay, times U, where U is in SU2. Okay. Now, let's look at that. So now let's expand the U around identity. So you will find here e to the I theta, so we want to expand U hat around identity. U hat expand U hat around the identity. You write it as 1 plus plus whatever, some order epsilon times m hat, let's say. Okay. So since I can express this in terms of that, so what does it mean? I'm writing, so u itself has to be 1 plus epsilon m, okay, plus higher order. But the phase e to the I theta, you see, if it was identity, then the phase has to be 0. I mean, e to the I theta should be equal to 1, because the first term is 1, right? So I can write this as, this itself as 1 plus I times epsilon theta. Right? The theta itself is small. So think of this as a small, very small parameter, epsilon theta. So I can expand it. Okay? Is that clear? Okay. Yeah.
My question was, I was wondering, because in HEP-2 we have 4 parameters and 1 condition. I mean, the one restriction, this S3, where here we have n, we have 4 parameters, and then when we use the determinant, we have 3. I was thinking, why we couldn't have 4 parameters and then we have one restriction?
Yeah.
Sure. And we could use all the matrices and the derivative, or it's just because, or just we have 3 parameters? There's another way to see that?
Yeah, I mean, well, okay, the 3 parameters, but true. I mean, but it could have been that maybe one of the sigma is not entering, identity is entering. You know, I mean, there are 4 parameters, right? One combination should not be here. But which combination? Which combination? That is precisely this identity combination. You see, and that is from this argument. You see, because this we said is a SU2, right? So this epsilon m. So the trace of m should be 0 and m should be anti-Hermitian. So this tells me that this guy is linear combination of sigma a, right? Some xa sigma a, not of identity. Right? So we have this. But then I had the determinant part which was coming up, this phase which was coming here, this 1 plus I epsilon theta. Okay. Now open it up and collect all the terms of order 1. You see, order 1 term. So this will be equal to 1 identity. This is 1 times identity, plus order 1 term, this identity, will come from this times that, which is I epsilon times sigma times identity. Okay, and this times that. So here is epsilon here. So plus I epsilon sum over say sigma. So you get back the full thing. You see, that identity term which was missing in the SU2, you get back in the U2. Yeah. So that is what. So really, this is the determinant part. This really controlling the determinant. How determinant is away from 1. If you know. So this is so the U2 will have 4-dimensional generator. Generators will be 4, sigma A and identity. Whereas SU2 will be just sigma A.
Okay, thank you.
Okay. I also have a question. When you say that the Pauli matrices are a basis for the group SU2, you mean a basis like any matrix in that group you can write as a linear combination of them, but there is no such a restriction, like for example that the components of the basis are orthogonal or something like that, or that basis definition just means linear combination of. Well,
okay. First of all, let me say, it's not the group elements. What we are talking about, the generators. So, I mean, when you take linear combination of some basis, that makes sense only for a vector space. You know, if your space is a vector space, so that it makes sense to add 2 vectors and you get a 3rd vector. No, the group itself, in fact, we saw is not a vector space. It was a S3. There was no notion of adding 2 vectors of S3 and getting another point in the S3. No, S3 itself is not a vector space. Group space is not a vector space. But what is a vector space is the generators, is the tangent space. In fact, that is what we'll be discussing next time. You know, what is the geometric interpretation of these generators? It is true that even though group itself has no vector space structure, but when you restrict yourself to the infinitesimal generators, they have a vector space structure. You can talk about adding, you add 2 of them, you get again another third generator. Huh? So that, but was that the question, or maybe I misunderstood the question?
Yeah, just that if that definition of basis was just that any matrix in the group can write as some kind of combination of that matrices.
So not the group, but generators, yes. The group is not, there is no linear structure in the group. No? Only when there is a linear structure, only then you can talk about vector space. So in the generators, so the statement is that any generator of SU2, no? Generator defined like this, meaning order epsilon term. So when you look at something which is very, very close to identity, okay, those guys form a vector space. Those matrices M, they form a vector space. And I mean, this also you can see, right? Because, I mean, look at this, say I take the product of it. So I have one U1 and U2, let's say. U1 is also close to identity and U2 is also close to identity, right? I mean, U1 times U2 is a matrix multiplication. No? There's no, this is a matrix, that's a matrix, there is no vector space structure. No? There's no additive structure here. No? But when you write this U1 as 1 plus epsilon M1, 1 meaning identity, 2 by 2 identity, times identity plus epsilon M2. So this is U2. So both are close to identity, and order higher order, so plus higher order. Okay. Now multiply this, it's a matrix multiplication. So what do we get here? We get here identity. Identity times identity is 1, identity again, plus order epsilon term is this times that, plus that times that. So this is nothing else but M1 plus M2. You see? And then order epsilon. At order epsilon square, it's not linear at all. Because you see, let's say here it is some M1 prime, and here is M2 prime, epsilon square. So order epsilon square, when I open it up, I will get here M2, M1 prime, plus M2 prime, plus epsilon, plus M1, M2. You see, now there is no linear structure. The moment you go to quadratic term, because this is not linear. Whereas order epsilon is a linear term, you are just adding up these 2 matrices. That is why this is a vector space. This is a vector space structure. So you can, M1 is expressed in terms of linear combination of polymatrix. M2 is also a combination of polymatrix, or I times, more precisely I times polymatrix. Then the sum of them will also be linear combination of polymatrices, right? So that's why, the vector space structure appears only for the generators, not for the group. Yeah?
Okay, thank you.
Yeah. Okay. So so tomorrow I don't have a class, but tomorrow you have a tutorial. No? Aida will be tutoring. I don't know whether she contacted you about anything. Not yet. Okay.
Not yet.
Okay. So then we meet next Monday. Okay. So have a nice weekend, and probably I'll see you next week. At least those of you who are here already. So you'll be here then. Yeah.
Thank you.
Okay.
Thank you very much.
Professor, would you give us some homework for tomorrow's tutorial class?
The homeworks are all this. Whatever is given in the, I mean, there are lots of exercises here. If you look at already all the previous chapters, there are lots of exercises. So those are the homeworks. Exercise. Now I don't know. Aida has not contacted you. I think what she will do probably is go through the maybe the 2nd chapter and probably 3rd chapter. She will try to go through them most likely. I don't know exactly what her plans are, but she will tell you tomorrow. I mean, at the moment anyway, you are not here, but probably from next week you'll have to submit the homeworks before the tutorial from next week. But she will tell you all the rules. Huh? Okay. Okay.
Thank you.